Hello class, my name is Pablo Cetillos. Today I want to talk about Quaternions. In this PDF I have put together all information about Quaternions that is uh, related to the things that we have learned so far in this course. Uh, I will try to cover the most important things from this PDF uh, in less than 20 minutes or so. Okay, so let's begin. Definitions. Quaternions are essentially an extension of the complex numbers. Rather than introducing just one value, uh, I, we introduce three right now. We introduce I, j, and k, such that I squared is equal to j squared, which is equal to k squared, which is equal to -1. Moreover, we insist that these are different from one another, and we relate them as follows: I times j is equal to k, jk is equal to I, and ki is equal to j. And we have the first theorem. From the above rules, we get some other facts, like this one, and this one, and this one. And we have the proof, which contains a lot of expressions. This proof follows the rules that are here, so this is an easy proof. At this point, notice that, for example, ij is equal to -ji, so multiplication as defined is not commutative when it includes I, j, and k. As we will see soon, it's not anti-commutative either when we go full on with quaternions. So right now we have the full definition of a quaternion. A quaternion is a number of the form q equal to s plus ai plus bj plus ck, with s, a, b, and c real numbers. As you may see, this notation is very similar to the notation of vectors in R3, and later we will see why we have this notation and the relationship between quaternions and vectors in R3. We extend definitions, subtraction, and multiplication to the quaternions by obeying the above law, the above rules, as well as distributivity and associativity. We have another definition, another important definition. A pure quaternion, also called a vector quaternion, is a quaternion with a scalar part equal to 0. That is, we need s to be equal to 0. When s is equal to 0, we have a pure quaternion. Another definition: a scalar, also a scalar quaternion or a real quaternion, is a quaternion with vector part equal to 0. So in that case, we need to have a equal to 0, b equal to 0, and c equal to 0. The set of quaternions is denoted by h. We have an example. We have 2 plus 3i minus 1j plus 2k is a quaternion by definition, and 3i minus 1j plus 2k is a pure quaternion by definition, and the number 7 is just a scalar. We have another example. Suppose we have quaternions q1 and q2. Note that, and when we use the distributive law, we have this equality: 2 times 3 plus 4j plus I times 3 plus 4j. Then 2 times 3 is 6, 2 times 4j is 8j. I times 3 is 3i, and I times 4j is 4ij. As we learned before, ij is equal to k, so we have this last expression. So just to compare, note that k2 times k1 is not the same thing like ky q1 times q2. From this example, I want to mention again, we have that q2 times q1 is not the same thing like q1 times q2. And we have another example. We have two quaternions, quaternion q1 and quaternion q2. And when we multiply by using the distributive law and associativity law, we get this expression. So we have this theorem. Well, this is not a theorem, but it is important to have a special attention to the fact that quaternions, multiplication of quaternions is non-commutative. So right now we will study the vector connection. Okay, the use of the notation I, j, and k are not arbitrary. We can use, in fact, vector operations like cross products and dot products on the vector part of quaternions. For example, suppose we have q1 and q2, then if we use the dot product, we get q1 dot q2 is equal to 16, and the cross product of q1 times q2 is another pure quaternion. Not that we can do this because q1 and q2 are pure quaternions. They are vector quaternions. Many times when we write a quaternion q, we denote it by s plus b, where b is the vector part, or we write q equals to this expression, where s is a real number and b, well, b is a vector. We learned before that the multiplication of quaternions multiplication is not a funny thing. We have to do a lot of operations, but the interesting fact here is that the cross and dot products may simplify quaternion multiplication. We have this theorem. Suppose we have quaternions q1 and q2, where q1 is equal to s1 plus b1, where b1 is a vector, and q2 is equal to s2 plus q2 plus b2, where b2 is a vector, and s1 and s2, and they are numbers, real numbers. We have this expression: q1 times q2 is equal to s1 times s2 minus and the dot product of B1 and B2 plus S1 vector times vector 2 plus S2 times vector B1, sorry, S1 times vector B2 times S2 plus S2 times vector B1 plus the cross product of B1 and B2, and we also get this other expression, Q2 Q1 is equal to S1 S2 minus B1 dot product with B2 plus this last expression. The parentheses are here because I want to emphasize the scalar part and the vector part, the scalar part and vector part. We have also another theorem. Suppose we have pure quaternions B and W. So when we go to here again, we know that S1 for B is equal to 0 and S2 for W is equal to 0, and because B and W, they are pure quaternions. So then we have here 0, 0 and 0, and then we have B cross product with W minus B dot product with W, and similar results we have for W times B. We have another theorem, but this theorem is not very important. So now I want to talk about the conjugate of a quaternion Q, which is denoted by this expression, and is defined by S minus I minus A, sorry, I minus BA minus CK. So we have the same thing, but with the difference that we change the sign, and we can also write this expression because as we saw before, K is sometimes denoted by S plus B, where S is a scalar and B is a vector. We have this theorem, Q times Q conjugate is equal to this expression. Later we will see what does it means. Well, in complex numbers we know that this may recall the norm of a complex number. We have this theorem. If we have two quaternions, then we see this property. The conjugate of a product is the product of the conjugate in the inverse order. Now we have the norm, another important thing in quaternions, the magnitude or norm. We have this definition of the magnitude or norm of a quaternion is this expression. A definition again: a unique quaternion is a quaternion with norm 1. That is when this expression is equal to 1. Well, we have this other theorem, as if Q is a unique pure quaternion. Sorry, Q is a unique pure quaternion if and only if q squared is equal to -1. So proof. For the general quaternion, q equal to s plus b, we have q squared is equal to this expression. Remember that this expression comes from a previous theorem, where this is the scalar part and this is the vector part. So then we have 0 here because b cross product of b is 0, of course, and then we have this expression, right? So if q is a unit pure quaternion, then s is equal to 0, right? And we should have a s squared plus b squared plus c squared equal to 1. And so then the result follows immediately. Because we have 0 here, 0 here, 0 here, and we have -1 here, so we have this expression. So now, okay, on the other hand, suppose q squared is equal to -1, then we have the following: s squared minus a squared minus b squared minus c squared equal to -1. And we should have all here equal to 0, because now it is equal to -1, which is because it is equal to -1, which is a number, so it is 0 and it is -1. So we have this expression, this other expression, and this other expression, but that we cannot have s different than 0, because that would imply a, b, and c to be equal to 0. So that would imply a equal to b equal to c equal to 0 from here. But that contradicts this expression. So we must have s equal to 0, in which case we have this result, and therefore by definition the norm of q is equal to 1. And from this theorem we have that the norm is multiplicative, so the norm of q1 q2 is the product of the norm of q1 and the norm of q2. Translations. If a point xi plus yj plus ck is to be translated in 3D space, we simply add or subtract another pure quaternion. For example, suppose we have this quaternion on this point, and we want to translate it by phi in the x direction, 2 in the y direction, and 7 in the z direction. So what we do is we write the point, or the quaternion, the pure quaternion, and we add another quaternion with phi here in this place, 2 in this place, and 7 in this place, and we get this point, which is the result of translating this point by phi in the x direction, 2 in the y direction, and 7 in the z direction. Now we have rotations, so we can do rotations about the lines through the origin. Lines through the origin can be represented by vectors, direction vectors, and we have this theorem Suppose we have the unit vector u and the vector b, and the vector b can also represent a point in R3, and the unit vector u can be the direction vector of a line through the origin. Then we have the result of rotating the vector b or the point b around the unit vector u by an angle theta counterclockwise with regards to the right hand rule. So then we have the result of rotating b around u by a angle theta counterclockwise regarding the right hand rule. And that result equals to this expression. And we have the proof, but this proof is very large. So, but visually, we want to say that if we have this line, then we have this vector, and we want to rotate this vector by theta, and then we get this other vector, which is equal to this expression. Now we have this theorem. Suppose we have the unit vector u and the vector b, and the result of rotating the vector b around u by an angle theta counterclockwise using the right hand rule can be obtained by letting p equal to cos of theta divided by 2 plus sine of theta divided by 2 times the vector u, and then doing p times p times p to the negative 1, which is equal to p times p conjugate. And we have here the proof, but this proof involves many expressions, and we don't have time to do that. And we have here an example. For example, in order to rotate the vector b equal to 2i plus 1j, or the point 2i plus 1j by the angle pi divided by 3 radians about the normal vector u, we set p equal to cos of pi divided by 6 plus sine of pi divided by 6 and times the vector u, which is equal to this expression. And then we do the following: p times b times p conjugate, and we have a lot of operations, so we use MATLAB, and then we get this point or this vector. This is a picture of the last example. We have here the point b or the vector b, and we have the unit vector u here, and the resulting vector here. So you can see that this point is actually is the result of rotating this point by pi divided by 3 angles through the unit vector u. So the calculations are right. Okay. Rotation about lines not through the origin. Okay. To rotate about a line not through the origin, the process is simple. We take a point on the line, any point on the line, and translate that point to the origin, then rotate, then translate back. And note that the direction vector from the axis for the axis doesn't change. Thus, if we have a line containing point b naught with unit direction vector u, then rotation about this line can be done by this expression. We subtract b naught to b, and then we this quantity we multiply this quantity by p and p conjugate, and then we add p naught. And remember that p has before for rotations, and remember that p is a unit quaternion. Now we have reflections in planes through the origin. We have this theorem, and suppose we have a plane P through the origin represented by the unit pure quaternion or unit normal vector n, and then we have that we have the reflection of the vector B is given by this expression, and we have here n. We have that B goes to n times B times n, and it is important to remember that n is a unit normal vector. We need here a unit normal vector. But if we have n not normalized, then to normalize we just divide by n by the norm of n squared, and we are okay. We have an example here to reflect the vector b in the plane through the origin with normal vector n. We calculate the following, and here we have vector n, vector b, vector n again, and here we have 1 divided by 3. Note that the norm of n is equal to 3. So that's why we have 3 here. And then we have this vector or this point. Here we have the picture of the last example. We have the vector or the point B here. We have the normal unit vector here and the plane that is represented by the normal vector n, and then we have the reflected point here. You can see that that the calculations are right, because well, the picture seems pretty good. The last thing that I want to talk about is reflection through lines in the origin. We have this last theorem, giving a line L through the origin represented by the unit pure quaternion. The reflection of the vector n is given by this expression. We see here that B goes to negative u times b times u. So this expression is very similar to the previous theorem. If you read this proof, you will notice that there is a reason why this expression is very similar to the expression of the last theorem. And we have a picture here where the vector u is the direction vector of a line, and we have a similar expression here when this u is not normalized. And this PDF contains many other transformations of lines and planes, and transformations of and a lot of exercises. Unfortunately, we cannot cover everything here because we have we don't have a lot of time. I want to end with this summary. We have a cover here. We have a study here about the rotation about a line U, reflection in a plane, and with normal vector n, and reflection in a line with unit vector u, and we have the expressions here. And so that's all. Thank you for listening. Bye.